So let's get going from a review from last time, because sometimes it's good to page back in what we learned. Okay, so I asked you a couple of trivial questions. One of those questions was, what is a computer program? And really, I meant, what is a computer program as we're going to think about it in this class from the perspective of a computer? So what was a computer program? Let's get in the habit of just shouting out things that are, maybe even obvious, and it'll just keep the... So a list of instructions, or if you want to even, I could ask you what's an instruction. If we want to be more abstract, it's a list of commands. A program is a list of commands telling the machine you will do this, you will do that, right? So it's I have here the slides of a list of processor instructions. At the end of the day, this program text turns into a list of commands. Okay. All right? And what did a processor do? Given a list of commands, what does a processor do? It executes those commands. I'll give you that one. But when we talk about executing the commands, what are the effects of those commands? What do they do? Modify state. And we talked about two types of state, right? We talked about registers, and we talked about main memory, right? So this processor, it executes instructions. I gave you this really simplistic notion, just enough detail to help us think about it. It's useful to think about, there's components of the processor that are about control. Given the program, what do I do next? Like, what's the next operation? Or if there's like a branch, where do I go next? I typically just have that as my orange boxes here, fetch and decode. Then you have a part of a processor, some of the hardware that's actually responsible for doing stuff. So I'm calling that the execution unit. And we have two forms of context. We have the register state of the processor, and then not shown on the diagram, we have memory. Right? And my simple processor last time was going to execute one instruction every clock tick, making progress. Right? But then we said something else. We said, well, if we look at the instructions in a program, if we look at those instructions, and this was a larger program, we can take a look at them and say, not all the instructions depend on the previous one in the sequence. So this was a sequence where I really recommend that you go offline and confirm to yourself that if these are the numbers of the instructions, and I'm representing those instructions as a node in the graph, there are certain dependencies. I have to do instruction 2, for example, after I do instructions 0 and 1. Because I can't add two numbers if I haven't brought them in from memory or something like that. And so we said that, in the same way that you can look at this program and go, I know I'm supposed to get an answer that's the same as if I ran these all serially. But if I had extra resources sitting around, I can do some of these things in parallel without really telling anybody that I changed the order, and they'll never know. All they'll see is that this program goes a little bit faster. And so we talked about this one idea last time of superscalar execution. And if you break down the word, it's kind of a weird word term, but if you think about it, it's like scalar execution, which is like doing one thing at a time. And then the superscalar is kind of like a fancy, technical term for saying, we're actually doing a little bit more than that, but your program is still saying I'm doing one thing at a time. So it's something that's going on under the hood. So this was the first thing that we talked about where there was a little bit difference between the abstraction, the meaning of a program. A program is a list of instructions and says if you perform these operations on this state, at the end of the day you should get this answer. Then there's the implementation in a modern processor that says, we can do them in a little bit different order. It'll be better for you, and you'll never know. So that was a little bit what we talked about with processing. We also talked a little bit about memory, and I asked you what was memory. So in the same way, if I ask you what is a program, it's just a list of commands where those commands modify state in a machine. What is memory? Yeah, memory is just, logically, abstractly, it's just an array of bytes. It's part of that state for that program. And if a program says, please read the value at address 42, memory says, well, address 42 has some value, and sure, I'll give you that value. Right? If a processor says, write the value to address, write the value foobar to address 42, well, memory says, okay, I'll take in that value and I'll put the value foo bar there. Okay, so we talked about memory just being a big array of bytes. But we didn't talk very much about, right, and I even showed you, but we didn't talk very much about implementation. So notice how I'm setting this up over and over. There's what something means, it's semantics, like add these two numbers, then add those two numbers. Or there is an array of addresses, and every address has a value. And then the underlying implementation of that. Okay? So if I tell you memory, many of you might say the word DRAM, or remember a big stick of memory that you might have shoved into a laptop at some time, or something like that, right? And so what a DRAM chip does is it provides, it's the implementation of this abstraction. You send that DRAM chip a command that says, give me the value that's stored at address, hex B, and this memory chip will send 255 back. But we talked about last time how it could take a while to go get that message out there to memory and come back. And so all modern systems have some form of a cache. And this cache is another form of storage that's part of the implementation of memory. But if the processor says, I need address 4, well, that value might be stored in cache, and it can get the answer much, much faster. So that was kind of right where we left off last time. Any questions? Just trying to, I often overlap just a little bit because it's good. Yes, sir. Oh. Dynamic RAM? Yeah, just dynamic RAM. And it's dynamic in that if you cut the power, as opposed to something that's persistent, like SSD or embedded. Mm-hmm. Okay.
Even if you read a value.
That's true. Even reading a value destroys the value. So when you read a value, you actually got to put it back. Otherwise, you lose it. But for fun, we actually have a 30 minutes on DRAM, very, very much at the end of class. But for now, you should think about it as it's far away. And since it's far away, it's like it's standing in the back of the room, or it's storage in your garage or something like that. If you want to go get something there, it's going to take a little bit. And you should think about the cache as like what's right on my desk.
Addresses that you've listed out, the existing one would be right?
Don't think about implementation. They're just addresses. I have something, I have this concept. I have memory. Memory takes a value, an address, it gives you a value. DRAM is one way to implement that. A cache is going to be another way to implement that. And this is something we haven't stressed very much in the class in previous years, and so this is kind of, we're trying to set the stage a little bit more this year. So there's two kind of details of how a data cache works that are kind of useful to think about. One is, even though memory says if you give me an address, I'll give you a value, the underlying implementation in any modern system that I know about will move data from memory into the cache at some larger granularity of cache lines. So in this figure, this cache holds data for 2 cache lines. Each of those cache lines is 4 bytes. So the bytes store, beginning at address 4, so 4, 5, 6, 7, these are the values out in memory that are replicated in the cache. You should be able to confirm that if I did not mess up my figure, right, 0060. Okay? So this is a cache that has the ability to replicate 8 bytes. It's organized into 2 cache lines of 4 bytes each. And what I'm highlighting in red is sort of the place in the address space that corresponds to these 2 cache lines. I've seen a bunch of questions, yeah.
Address you want to fetch. And if it's 0x5, will we just fetch the next 4 addresses up to 0x5?
Yeah, good question. Think about you're going to access and move data from DRAM memory onto the chip in the granularity of 4 bytes rooted at address mod 4. So if you want address 5, the actual command out to memory is give me the cache line of 4. Yeah. Yeah.
Do different execution units have different caches, or is there a...
I'm not going to answer the question just yet. I just want everybody to learn it for one processor just yet. Absolutely, yes, but and you're probably already thinking about how the heck if I replicate data all over the place, how do I keep things consistent? You are correct, but not today. Yeah.
Keep DRAM so far away.
Why not put a garage on my desk? Cool. Yeah.
Sorry, maybe you could explain one more time exactly what a cache line definitionally.
Yeah, sure. So what is memory? Memory is an address space and a value at every address. Somehow we have to implement that. So somewhere in the system, I need to have storage for every address. And typically, that is your off-chip memory these days. Okay. Now, a cache is just keeping a copy of this information right on my desktop. Okay. Now, the organization of almost any modern cache, anything you get on any chip that you're probably going to run, is that data is going to move between memory and the cache at the granularity of lines. So on an Intel chip, that's a 64-byte cache line. On my diagram, it's a 4-byte cache line because I didn't want to draw 64 numbers. Okay. And so if you want address 5 in my cache, you're going to go ask memory, give me all the information for the line starting at address 4. Does that make sense? Yeah. Okay. And next slide, I'm going to get into why we work at granularity too. Yeah. Okay.
The starting address from which you take things is basically always multiples of 4 or multiples of
cache line size. Multiples of cache. Yeah, we're going to work at that because we don't want to have a dynamic allocation situation here. This is going to be hardware. The whole point is to be able to access. Like when this processor says I want address 5, and we say load address 5. Okay, here let's think about this. What happens if the processor says, I want to load address, actually I'm going to go with something else. Let's say address 5. Conceptually, it's asking memory, please give me the value at address 5. But what it's first going to do is it's going to ask the cache, hey, do you have address 5? And the cache is going to go, yeah, I do actually. It has value 0. Right? If the cache doesn't have the value, now we're going to have to go get it. And then the cache is going to ask memory, hey, can I get the line that contains 5? And that's when those 4 values come in this case. So let's think about it in a slightly richer situation. This is what we were going through right at the end of class. End of class, nobody knows, everybody's tired, nobody remembers anything anyways, so we're doing it again. Okay. So here is the value of memory. Notice that I'm really saying memory, and I'm not saying DRAM or any implementation, even though almost all of us, if we say memory in computer architecture, we're probably thinking about off-chip stuff. Okay, so this is just the state. This is the state of my program, these values. And here is a list of addresses that my program is going to access. So it's going to be like, I'm going to access address 0, then address 1, then address 2 in time. Okay? And what I'm going to show here is what is the cache doing in response to those processor actions. So let's say that the program says, please load the value at address 0. And let's just start from the place where there's nothing in the cache or everything's sort of invalid in the cache. Well, the cache is going to go, hey, wait a minute, I don't have that value. So it's going to go ask memory for a cache line. Or DRAM for, right, so, and these are my cache lines. Sorry, I didn't draw that for you, right? So when we say, hey, I need address 0, the cache goes, you've never asked me for that before, why would I have it? This term so it's a cache miss. The value is not in the cache. And if you read a computer architecture textbook, they taxonomize the reason for these misses. And so in this case, I wrote on the slide cold miss because we have never even touched that data before. There's really no reason it should be in the cache. So the idea is that the data is cold compared to data that's hot that you're often accessing. Okay. So notice what happened in the cache state. The cache now has one valid line in it, and it's the line beginning at address 0. So that may have taken a while. There might be some real latency in that operation. Now, what happens when the processor says, in some later instruction, sometime later in the program, the cache hasn't changed, nothing's changed, it's done no other memory, and it says, you know what, I want to read address 1. What does the cache say? Yeah, it says, I got address 1, that's a hit, nothing happens, right? So that can potentially be really, really fast. And the same is going to happen for 2, 3, and then what happens if I go back to 2? We're good. It's another hit. 1, another hit. 4, don't have that. That's got to get brought in. And now my cache in this example has capacity for 2 lines, so we'll just put that other thing in. When I go back to 1, what happens? I'm good. Exactly. So one thing I want you to take away from this slide is actually the cache is sort of solving 2 problems at the same time. I'm actually going to go to the second one first. The one that I've kind of set this up for is if you've already touched data, if you've already accessed data, the cache has it, which means all subsequent accesses will be faster. So in general, one of the big reasons for a cache is that if I'm touching stuff a lot, the paper that I'm working on right now, the homework that I'm grading, that's why I keep it on my desk. I don't take it to the garage every single time I want to look at it. Okay. So that's this notion of temporal locality, back-to-back accesses in time. That data's sitting there. So that's what's helping me with. It's preventing me from going out and looking at it. The other thing that you might have noticed is that this granularity of operating at the granularity of lines, first of all, bulk transfers are almost always efficient. So I can transfer data efficiently to the cache. But it's based on the assumption that if I access address 0, oftentimes programs then go access 1, 2, and 3 too, because they're like running right down an array, for example. Okay. So there's actually 2 forms of the way reducing latency here. One form is almost like the line is functioning as a prefetch for the next items in the array. The second one is by bringing the data in now, I'm assuming you're probably going to touch it again. Like a common thing would be to read something, do some logic, and then update it. So there's already two memory accesses. Okay. Now I want to throw out one more pattern for you, which is kind of interesting. Same cache, and now all I'm going to do is I'm going to read right down an array. Notice that the addresses are just increasing by a byte every time. Except okay. So let's just do this. So hit, right? Hit. Now what happens? Miss, good. Hit. But what do? My cache is full. So now we got to throw something out, right? And last time I told you that in this class we're going to assume a very simple policy of least recently used. There's some questions on the website about this. So the line that I have touched least recently, the longest time ago, is the one that I'm least likely, that's the assumption, to touch again. And in this case, what color would it be? Red. It's red. So we're going to drop red and bring in green. Okay, so this is a cold miss on green, right? Because I've never touched green before. It's the first time I've touched this data. So this will continue. Hit. Then we get to address 12 or hex C. It's another cold miss, and we got to throw out blue. Exactly. This question somewhere? Yes.
In computer architecture, isn't this called a capacity miss since you're throwing something out?
No, this is a cold miss. It's the first time you've touched the data. The name of the miss is relative to the data that I'm accessing. If we would have had an infinitely sized cache, I still would have missed here, right? It's the first time I've touched it. But your question is relevant now. So what happens when I go back? So here, look what's happened. I have already accessed address 0 right at the very beginning. If I had an infinitely large cache, or arguably a cache that could store 16 bytes, that would have been a hit. So that's a miss that occurred because of actually I even got that wrong. That's a capacity miss. Sorry, yeah, hold on. 1 second. Yeah, my bad. Yeah, so this is a miss that occurred only because a cache has a finite size. If I could have put my garage on my desk, I would have been, hitting on everything. Okay. You asked me about a capacity miss. A capacity miss is actually a miss that we will not talk about in this class, but comes from the fact that the cache might have been big enough, but the organization of where data goes doesn't allow the data to still be there. So we'd have to talk. What?
You mixed it up again. Conflict.
Oh, sorry. Yeah, that's fine. Yeah, sorry. A conflict miss is one where the organization of the cache means that, like, hey, I could have put it somewhere if I could have put any data anywhere in the cache, but increasingly large caches tend to have policies that say this data can only go here and this data can only go here. Yeah.
Besides the change in names, is there anything different when it comes to this miss than the other misses? Like,
there's only no. I mean, the name is giving you a reason, and really, if you think about it as, so when you evict something, when you evict a line, your behavior will be different based on whether or not that line has been written to. Because if it hasn't been written to and only read, you just toss it. If it has been written to, you got to push that data back out to memory. So that's the biggest difference. Yes.
Address in order. I put it like after 0 times 4, that address will be after 0, after the fourth
So we
line.
go 0, 1, 2, 3, 4.
Yeah, and then we do it 0, 5, skip the 0, 4.
Uh-huh.
I wonder like what will happen and with the non-through line go from 5 to...
No. Okay, so and this would be a good thing for you to just work out. But what I do want to say is and this is similar to the earlier question. The mapping of cache lines to addresses, that is fixed. A cache doesn't even think about addresses really. It thinks about cache lines. And so I've just divided my address space up into these cache lines, mod cache line size. So if you decided to go, I want to read 0, 1, 2, 3, 5, 5 would trigger a load of the blue cache line. Mm-hmm. Yep. So what you've done is you've actually reduced the spatial locality of your accesses. So if you did 0, 1, 2, 3, 5, 6, 7, 8, 10, you just would be loading 4 values in this case, the cache line, and never touching one of them. Right? So you're incurring memory traffic or communication that you didn't need, but that's just the way the underlying implementation works. Mm-hmm. Okay, I'll take 2 more questions and I'll keep it moving. Yeah.
I'm wondering if you could say a little bit more about the difference between a capacity miss and a conflict miss.
I'd rather not right now, actually. Yeah,
We'll come back.
I don't believe that anybody has had any kind of set of sensitivity or that kind of stuff. So I'm not. You're asking questions about how to design real caches now, and yeah.
So maybe I'm belaboring the point, but when we talk about capacity miss and code miss, the processor doesn't know it was a capacity miss.
Doesn't matter. Yeah, maybe in hindsight, maybe I should have said miss. but for the sake of the class, it's a miss. Either way, it's I don't have the data. I've got to go get it, and I need to invoke my eviction policy to figure out who's leaving. Yeah. Mm-hmm. The reason for that doesn't matter. The only thing that the reason matters for would be like you might be able to, like, if you knew the reason, you might be able to change your program a little bit to avoid the miss. Okay, all good? All right, last one.
Is there, what's the overhead for like loading the cache line? And if there's a significant overhead, is there like a ratio of like loads and like cache line hits that you need in order for it to be like time economical?
We're gonna slowly graduate towards all that because the reason why I'm spending all this time on a cache is for those kind of reasons. But the main thing that I want you to take away is that caches exist. They're an implementation detail. If I took the cache out of a computer, you would get the same results. It just may run slower, right? That's the most important thing. And the caches exist to reduce the latency of memory access so that this processor is not waiting. Now, under the hood, if I had to elaborate a little bit more, in the same way that like I have a desktop, a filing cabinet, a hallway closet, and a garage, and I put different stuff in those different storages based on how often I might need them, most modern computers have a hierarchy of various caches. And I think a reasonable rule of thumb is that if a unit of storage is bigger, it is farther away. It has higher latency to access. And we'll also talk about how it actually has higher energy to access and stuff like that. But for example, if you rip open most modern machines, you usually see like a L1 cache that's pretty small, a few kilobytes, right next to the processor that can be accessed in a few cycles. If you miss the L1, you'll ask the L2. If you miss the L2, often you'll see an L3. And if you miss the L3, you'll go out to DRAM. And this is something I showed you to finish class up. You started to hint about what are the consequences of missing. So this graph is to scale of the number of cycles a few years ago now on Intel CPUs that it took. If you issued an instruction, how long would it take to get the data? And an L1 cache hit was about 4 cycles. Pipeline, so you can actually really cover that. Like if I did it in animation, not that fast. If you get it out of the next level of cache, it's going to take a little bit longer. The next level of cache, it's going to take a little bit longer. And if you miss this cache hierarchy, you're waiting. You're definitely waiting. So consider a system that's like load, do some math, load, do some math. We're worried about using 4 cores, getting a 4x speed up, and if you get your memory wrong, you could potentially be off by a factor of 250. Okay. So the scale of these effects that deal with data movement are enormous. Okay. So I want you to that's like us finishing up last time. Yeah.
One question is like you're taking it from RAM, you're putting it into L1. Is that like putting it into L1?
Well, that's the latency that I'm talking about. Like think about it this way: is if the data is in DRAM and the processor says I want address X. Let's think about moving it from DRAM into the L3, bringing it from the L3 to the L2, L2 to the L1, all the way to the processor. That's 250.
Is there no way to just bring it directly to L1 and just directly?
There are ways. Yeah, there are ways. There are instructions you can say is read this data, and I want you to bypass all the caches. I don't think they're as much about reducing latency as they are about not polluting your caches. I have a feeling like it actually probably goes through the whole path and then just doesn't get stored. Would be how I would implement it, I guess. Yeah. Okay. Oops. Shoot. All right, I'm going to re-emphasize this, but apparently Keynote won't let me go through until the animation is done. Yeah. While we're waiting, yes. Go ahead.
So it's not simply just read the data in DRAM instead of just update the data.
Yeah, that was the question here. Is like, are there really any benefits on a modern system of bypassing the whole thing? They're not going to be latency benefits. They're not going to be latency benefits. Okay, so I wanna let's put memory aside. It's coming back at the end of the day. But now let's go back to processing a little bit. So the rest of the lecture is going to be talking about kind of 3 major ideas on parallelism, on how we start adding more and more capability to do more stuff into a machine. And we're going to come full circle and end up saying some of these ideas are about combating this latency problem. So I already gave you caches as one way to combat the latency problem. Okay, and then so here's an example program that I'm going to use as the running example for the next 50 minutes, or the next 47 minutes. Okay, this is some straight line C code. Take a look at it. Make sure you know what it does. What it does is it takes as input an array X. It reads values, n values from the array X. It writes n values to the array Y. And what it does is for every input value X, it computes the sign or approximates the sign of X, given a numerical approximation using the Taylor expansion. So that, like how it computes the sign of X doesn't matter. The only thing that matters really is you look at the C code, you go, okay, I've got a piece of C code for I equals, outermost loop for I equals 0 to n. For every input element, perform a computation that ultimately computes value and is stored to the output element. The inner for loop is just an iterative algorithm to approximate sign. So what this is doing doesn't really matter. You could just think about this as some function that takes as input x sub I and outputs sign of x sub I. Any questions about the code? Does anyone need any more time to? Okay, so that's all I want you to think about. And my illustration on the right just shows you all the input values of x and the output values of y. Okay, right. So it just does that. Okay, so if we compile this program, we run Clang or GCC, pick your favorite compiler, we're going to get out a sequence of instructions, right, for this program. And I want you to kind of focus on the sequence of instructions that's the basic block inside the for loop. So we're at the moment we're going to think about, there's a sequence of instructions that says, once I load x sub I, here's all the stuff I have to do to produce the value that is then stored to y sub I. And now, given that sequence of instructions, we're going to execute it, right? Like, so that sequence of instructions, the processor is going to say, okay, what's the next one? Oh, it's a load of this value, then there's a multiply, and so on and so on. It'll run those instructions, it'll produce a value, and then at some point at the end of that, there will be a store instruction, which says store this value to the address given by x sub I. And just to repeat myself, if that processor is smart, it might look into that program, into that instruction sequence, and go, yeah, there's some of those instructions that can be done in parallel, right? Like, let me back up and let's look at it. Like, we certainly can find some stuff, right? Like this, computing the numerator is independent of computing the denominator, right? So there's a little bit of instruction level parallelism there. And so one way for me to run this program a little bit faster would be to take the superscalar idea. I'm going to build a processor. It still has like one set of registers. It has access to memory. But it has the ability to kind of figure out if there's two instructions that can be done in parallel, and it has two execution units to do them if it wants to. Right? Again, like you compile your program in C, you see a sequence of instructions. Processor, Intel does this, or AMD does this under the hood, you never know. Right? But in this program, or at least in this region of the program at least, there's not any ILP, like just in those instructions that I chose, they are all dependent. So this processor, if it was running that sequence of instructions, is only going to be making use of one of these execution units and one of these fetch and decodes, right? There's no ILP here. So this gets back to the broader thing. But there's tons of parallelism in this program, right? Because we can process every element of this array completely in parallel. But if all the processor is doing is kind of looking at like micro instruction sequences, all it sees is dependent instructions. It doesn't have the ability, or it would be intractable to kind of to have the ability to look over a huge window of the program, like that outer for loop, and go, oh, even though this is a for loop in C++, and technically every loop iteration is dependent because there's I++, they all seem to be accessing different input variables. That's the type of analysis that goes well beyond what could happen in a clock tick in hardware. So what hardware architects did is they said, you know what, let's just assume that the programmer tells us where that parallelism is, so we don't have to work so hard for it. So this is, I made that diagram that I had on the last slide just a little bit fancier. I said, look, you had this out of order execution logic. Outside of this class, there's all this other fun stuff that's in a processor to make an instruction stream go faster. A lot of it's about not accessing memory. Like you might put a big old data cache that has a ton of transistors to hold a bunch of data on cache. You might actually have logic that predicts what memory you're going to access in the future as a prefetcher. They had all this fancy stuff in there to try and make the inner loop go as fast as possible. But there's this outer loop that's trivial to parallelize. So idea number one is, let's take some of this fancy stuff out. Maybe a little bit smaller data cache. We're not going to maybe do as much out of order execution or anything like that. And if we clear all that stuff out, we just have our basic processor with just a few, which needs far fewer transistors. And I'm going to use all those transistors I have on a modern chip to just make more of to just replicate this, to make more of these processors. So now I have a processor, but it's a parallel processor. And this is, I'm going to use the term core, but there's nothing precise about this in the industry. So now I have a multi-core processor that just duplicated everything that was needed to run one instruction stream. So if I give this processor two instruction streams, and say, hey, core 0, run this instruction stream, and core 2, do that instruction stream, I might be better off, right? Like, for example, maybe these cores, because they don't have all the fancy stuff in them, can run one instruction stream 25% slower, right? Maybe they take more cache misses because the cache is smaller. Maybe they mispredicted a branch or something like that. But now, with those same resources, I could have 2 of these things. And if I put both of them running on different elements of the array at the same time, I have a 2-core processor that might run 1.5 times faster. Okay, I see some questions. Yes?
Can you talk about the execution context? Like, how many duplicated registers here? What's
Yeah, we just duplicated everything. We duplicated the hardware for executing instructions. We duplicated the registers. There's an R0, R1, R2 here. There's an R0, R1, R2 here. And there's the ability for each of these processing cores to take a look at the instruction stream that they're supposed to run and say, my little exec unit here needs to run this instruction next. And if that instruction is multiply R0 and R0 and R1, that's modifying this in these registers.
I just think compared to what I'm used to, right, there's easy actually code execute min right. And so having the execution context, I'm not sure if that counts.
Yeah, we're duplicating everything. We're duplicating everything. Yeah.
So talking about the resources you just mentioned, so like earlier, so basically using two transistors, you have an option. You can either create a superscalar processor or create a 2 cores.
2 simpler, yeah, exactly. Now notice that both my multi-core processor and a superscalar processor both have 2 fetch and decode units and 2 execution units, right? But I've decided to organize them a little bit differently and now duplicate the execution context. So I got rid of all that logic to try and find ILP. I got rid of logic maybe to have a really big data cache to avoid stalls. But now I have the ability to, if you gave me 2 instruction streams, I'll guarantee that you'll run both of them and get double the performance. Yeah.
Compiler can find out that the outer loop is parallel, right? So can you consider some of the instructions that...
It could. But then it's only working on stuff that it knows statically. In this case, modern advanced compilers probably could. But the minute I throw a small wrinkle in that program, the compiler's going to go, I don't know, I can't reason about this anymore, and we have to rely on the hardware. Yes?
But could you trivially just start it by just saying that, okay, instead, I'll just do it in chunks. So, for I and okay, instead of doing
Hold on. I love these comments because it's fun. You say, can't you trivially just do it? That's the point. In a program like this, which looks a lot like a tensor operation, right? It's trivial for you, the programmer, or maybe even a software compiler, to generate code that says, this is different from this. It's parallel, trust me. We don't need to rely on hardware to do it. So the observation is that doing that automatically in hardware is not an efficient use of resources. What's better is to push that up the stack. Okay? Now, right now, this is C code. This is valid compilable C code. If you compile it, Clang will kick out, unless you're turning on some very fancy stuff, a single instruction stream because the semantics of this program are serial. Okay? So if I take this program and I run it on my dual core processor, I'm going to create one instruction stream to run on one of those cores, and those cores are wimpy cores. It's going to run slower. Does that make sense? Okay? So I've got to change my program. So let's do it in the only way that we know how, assuming that you've taken 111, is let's spawn some threads. So take a look at this program. Take a break. I've been talking a lot. Talk to your partner or your friend or your enemy or whatever for 45 seconds, and I want you to tell me what this program does. And specifically what I mean is it computes the same answer as everything I've shown you. But there's 2 threads. There's the original thread and there's the thread that I spawn. One thread deals with some elements, another thread deals with some other elements. What thread does what? Take 30 seconds to just talk that over. All right. Somebody tell me how does this program divide the parallel work? Yeah.
So the main thread does the second half of the work, which is sin x. The main program does the second half, and the thread does the first half portion.
Yeah. So I have 2 threads. They both call sin x. The main thread actually works on the pointers at x plus n, which is actually n over 2 args n. So the thread I spawned does the first half. The thread that I already had does the second half. Okay? That doesn't matter. What does matter is, as the programmer, I've created 2 threads. And from the programmer's perspective, a thread. From the machine's perspective, 2 instruction streams. The operating system here, which we're not going to talk about, just says, oh, look, here's a program with 2 threads, 2 instruction streams. Hey, processor, here's 2 instruction streams. And the processor goes, okay, I'll run one on core 0 and the other one on core 1. Okay? But without me explicitly creating parallelism, or some magical compiler explicitly creating parallelism, this processor is not given 2 instruction streams to run. Now, another way to think about this is you're like, gosh, like this is kind of gnarly. I even had to ask you to parse the code. Really, the way you want to think about it is like, if I go back to the original program, you'd probably be like, it's a lot more intuitive just to like have some way to say that outer for loop is parallel or is independent. Like by saying, look, everything in this outer for loop you can do independently on different threads if you want to. You go figure out what thread should do what. And so you should assume that in modern programming languages, whether it be like PyTorch or any kind of programming language that has parallel constructs, there's almost always some way to have some form of a for loop, an iterator, where you, the programmer, declare, trust me, I know you can do all the loop iterations in parallel if you want to. Okay, so what I did here is I made up syntax. This is not valid C anymore. And I just said, imagine a for all loop where instead of saying I++, instead of empirically saying here's how we iterate all the loops, I just said, look, there's a for all loop. There's going to be n iterations. You can identify your current iteration by the variable I, and I guarantee you that I wrote the program. I know that all those iterations are potentially parallel. Like you can do them in parallel, and you will get the same answer. We're good. And if I write code in this higher level of abstraction, shoot, like it's not hard at all. All of you could sit down and go, I know how I'd do that. I would actually, like if I was running on a machine with 2 cores, I would create 2 threads, and then I would create a for loop on each, and one of them would do half. You could kind of think through how you would transform this program into this program if you knew you were running on a 2-core processor, right? Now imagine we weren't running on a 2-core processor, you were running on a 4-core processor. If you wrote code with p-threads like this, you would be like, shoot, I'm only actually going to use 2 of those 4 cores. Whereas that's why it's kind of useful to sort of think about how the programming model can give me a much more abstract way to just say, this stuff is independent, and however you want to schedule it in parallel, you can. Because if I start writing code like this, if I happen to run on a 4-core machine, under the hood, that runtime can spawn 4 threads. Or if I'm running on a 16-core machine, it can spawn 16 threads. I don't need to know as a programmer. All I'm doing is I'm saying, trust me, these iterations are independent. Create as many instruction streams as you feel appropriate on the computer that you're running on. Okay? So I can scale up to a lot of cores pretty quickly if I take out a lot of the fancy stuff. If I start like getting rid of a lot of IO superscalar execution, if I kind of maybe move to smaller caches, I do all the things that architects have done to make single instruction streams run fast. I can rip some of them out, and in a modern era, I can get a lot of cores on a chip. So, here's an Intel CPU. If you look at a chip diagram, you can kind of just see where the transistors for the various cores are. That's a 10-core Intel. This is actually the RTX 4090, and if you look closely, the replicated unit is about this size. There's about 144 of them on there. NVIDIA likes to call them SMs for shared multiprocessors, but that's the granularity of the duplication. Pull out your iPhone, and if you look at Apple's Bionic chip, there's 6 CPU cores in there. They're actually heterogeneous. They're not even the same design. So you have 2 cores that are bigger cores that have more of the big caches, the out-of-order execution in order to run single threads fast. And then for stuff where you have more parallelism, they have additional 4 small cores where more of that superscalar stuff has been ripped out and things like that. Okay. All right. And yeah, we've kind of already discussed this a little bit. Okay. So I said that like if I write code in this kind of manner, I said here's what we need to compute, but here are the computations that can be done independently. There's another property of this code that's pretty nice. I'm saying that everything that is being done independently, it's actually doing the same thing. The body of the loop is being done, the same body of the loop is being done by all threads if I executed this thing. The only thing different is that they're loading and storing different values. Okay? So that gets me to the next major idea here. So what folks said is, in a lot of these modern applications, machine learning for sure, graphics for sure, any kind of numerical computing or data science or anything like that, you're often working on code that looks a lot kind of like this. Like I've got a big array of values, I've got a tensor, I need to do the same thing on everything. So what they decided to do is now there's a change to my diagram, no change at all to the orange box. There's still a processor that grabs one operation per clock, can kind of like do the control, like, okay, what is it? Oh, it's an add. Oh, it's a multiply. Oh, it's a load. But now I've actually replicated my ALUs. So I have 8 ALUs on this diagram, or 8 execution units. And what's going to happen is that, like, if the next instruction is an add, we're not just going to do one add on one value. We're going to do 8 adds on 8 different values. So all of these are kind of locked together with the same control. And for now, one way to think about it is I also took all the registers, R0, R1, or whatever, and I turned them into 8-wide vector registers. So when I say add, so let's see here. So I used to have a program that when we compiled it, we would compile it to instructions that worked on scalar registers, like 32-bit values or 64-bit values. That's what the C code does. But now I have a processor that has the ability to run an instruction that runs on a vector of 8 values and should read and write vectors of registers. So one way I can get the compiler to generate these new instructions that I need is I can open up my favorite parallel programming library and I can change every variable in my program to the equivalent variables using these macros, these intrinsic macros, that every variable here is a 256-bit or an 8 by 32-bit float vector. Okay, so all I did is I rewrote the program where I took here an int or a float, and I turned it into a float vector of 8 things, or an int vector of 8 things. And then notice that my for loop, my outermost for loop, is not for I equals 0 to n, but I equals 0 to n by 8. So every time through this for loop, I'm actually doing the same logic, but I'm doing it for 8 things. Okay? And I've also made the code almost impossible to read. Right? Okay. Yeah, so this is so now when this program gets compiled by a compiler that supports these little macro functions, the output are instructions that modify vectors, not instructions that modify scalars. So you see the difference. I changed my R0s to these XMMs just to indicate that they were something different. Okay? So my compiled program processes 8 elements simultaneously using vector instructions with one instruction stream. So I still have one instruction stream, but the instructions now are these wide ones. Now I can combine that with multiple instruction streams. So if I take this new type of core and I apply it to my 16-core processor, I have a 16-core processor that runs 16 instruction streams, but the instructions in those streams are processing 8 pieces of data at once. So altogether, my chip has 16 cores, 16 instruction streams, 16 times 8, or 128 execution units, which means I can do work on 128 pieces of data at once. So arguably, I could maybe be going 128 times faster on the 16-core chip. Notice that you could imagine, if I asked you to, if you knew this was a for all loop, you could turn this for all loop, if you were a little compiler, in fact, assignment 1, you will do this, into 16 threads and those vector instructions inside those threads, and change that for all loop for I equals 0 to n to for I equals 0 to n by 8. So you can imagine how, if I asked you to do this in one assignment, the value comes from you being told what is potentially independent. The value is not from the mechanical transformation into vector instructions or threads. Question, yeah.
I feel like we're kind of like just taking through green that we can show all this into the registers. Is it just trivial then to fetch all of that?
Well, we're going to have some, we've got to move that data.
Yeah.
We are suspending disbelief temporarily on how costly it is to move data, and we're first getting set up on how to crank on that data. And then we're going to come back with the question at the end of, can we get the data there? Okay, so this was kind of like a pretty big intellectual change. I'd like everybody to this is a good time to raise your hand if you can't mentally think through what's going on here. Right, I have 16 threads running on a 16-core chip, and those threads, the instruction stream, contains instructions that are processing 8 wide vectors. And if I think of what's going on at any moment in time, there's 128 pieces of work getting done at any point in time. So if I perfectly parallelize and I compare my performance to my original starting processor that had 1 core and 1 ALU per core, I might be up to 128 times faster.
Could you repeat why putting them into a vector makes it faster?
Well, the first answer to your question is now I have 8 execution units that can do 8 things per core instead of 1 execution unit that can do 1 thing. Your real question is, well, why don't we just make 8 times more cores, right? And so what's going on is we're amortizing a lot of the costs of controlling or processing an instruction stream over these 8 execution units. And like in my cartoon diagram, notice that there's still 1 fetch and decode unit. Like you still do, what's the next instruction? Okay, that instruction, great. Now you're just going to say, I'm going to run that instruction on vector registers with my vector of ALUs. So this is a good idea because I can amortize the costs of the processor across many execution units. And I can do that if my code does the same thing. It needs the same logic for all of the elements.
In terms of resources involved, I think like a single, 16 single core processor, like single 16 core 16 core processors, I'm messing up the terminology, but basically 16 cores in that original.
You would be surprised, I know what you're getting at, how few resources are needed to produce an arithmetic unit compared to everything else, especially one that's not high precision floating point. Yeah. So the idea here is those things are cheap. We can pack a chip full of those if the code is set up to use them. That's the main idea. And now we're going to get to something that might, I meant to go this way. Okay. Now there's this question of, is the code set up to use them? So I'm going to change the example for just one slide. Imagine that this was my piece of code. For all n elements, do this logic. So for all n elements, every element can be processed independently. Do this logic. Read the value, and then maybe you need to do the if statement, and maybe you need to do the else. But I just built a processor that has, every core has 8 execution units that have to do the same thing. And now I have iterations of the loop that some of them need these instructions and some of them need these instructions. So I'm going to diagram this out for you as going down the slide is like time as we execute the program. Going across the slide is what each of the ALUs are doing. This is just about what's going on in one core. So at the beginning of the program, the ALUs are they're doing what I just told you. Like they loaded x sub I all in one big vector operation. They actually even can do the if t is greater, if for every iteration, if the value loaded is greater than 0. And they'll get a vector a bool vector of trues and falses as a result of those tests. Notice that some of these iterations evaluate to true and some of them evaluate to false. What do you think happens next? Any ideas? Yeah.
Trues and then only the falses.
Because the rules of my underlying implementation are I execute 8 things at once, and they got to be the same instruction. And in this case, what I might do is I might say, you know what? I know that this code that I have to run has to run the instructions in the if branch. So let's do it. Let's run those instructions in the if branch, and then let's just mask off or not even run, maybe cancel out the operation of any ALU that's responsible for data that actually doesn't need that instruction. And then we're going to run the else branch, and we'll flip that mask. And so at the end of the day, not all ALUs are doing useful work. I built this chip that has 8 things in it because I know that if I can do 8 things at once, I got a lot of compute for free. But if code isn't set up to do 8 things at once, I'm essentially just spinning my wheels on some of those execution units that don't have anything to do. Okay. Can you see why the worst case is 1/8? Right. Question? Yeah.
Shouldn't it always do the true case and then do the false?
Oh, I see. Well, first of all, 2 clarifications. Because if none of the iterations need the if case, we can be smarter about it and skip the thing. Yes, yeah. So here's a question for you. This is something to talk over. Can you give me the simplest piece of code that you can think of? And by simplest piece of code, I actually say, can you do it with one if statement? That overall, on average, this processor will be running at 1/8. Notice that it's not in this scenario, because it's running at 3/8 efficiency up here and 5/8 efficiency down here. Can you give me a piece of code that will create a situation where we're at 1/8 efficiency? Give yourself some time to talk about it. And you only get to use one if statement. All right. Any thoughts? Let's go to that. Yes, sir.
Could we take whatever is in the yellow block, put it into one equation and multiply it by t greater than 0.0?
Okay, say that again. So we have this code here, and what goes in the yellow box?
Yeah. So we can just multiply that by that Boolean statement above, plus that Boolean statement times whatever was in the else. So if it's true, it will be 1 times whatever's in the yellow box plus 0 times that thing.
Okay.
We'll have the proper answer, and then in the other case, it will be 0 times whatever's in the yellow box plus 1 times whatever's in the blue box, and then we'll get whatever's in the else. So you don't need the if statements.
You're trying. Oh, I see. Okay. So what you said was, I see what you're doing here. So I set up this thing where there's an if statement in the code. And what you're proposing is let's remove the if statement and the else statement altogether. The code is just the orange box followed by the blue box. And we'd get the same effect if we multiplied these results by 0 at the appropriate time and these results by 0 at the appropriate time. Okay, so that is a good implementation of this if statement. But what you've created is something that still does all the same instructions and has the same costs. So what you've said is if you wanted to compile this to a machine that has no if statements in the instructions, you actually given me a good lowering of the if statement to what's called predication. So good compiler optimization, but we're still running exactly the same performance as before. So what I'm looking for is a solution that, given that if statement, or given your implementation of that if statement, gets me running at 1/8 utilization. 100% utilization is every ALU is doing useful work on every step. 1/8 utilization.
1/8 at any given time, or 1/8 at all times?
On almost all times. Yeah.
Should you modify it to like if x at I is larger than x at I minus 1? Is then like the next branch has to depend on the previous branch?
So like x of I mean, there's no dependency. Well, there's a, but we don't know the values of the data. So what data would you give me to make that?
So yeah, I was thinking like you can do the same kind of thing, right? Where you load like the block into the vector register. But if the kind of output of each subsequent
but if you decide to put a sequential dependency between every iteration, yes, but by that definition, yes, you are running at worst case performance, but you've made the entire program non-parallel. I'm actually thinking about something that stays with the parallel program. Yeah.
Well, you just did if I is odd.
If I is odd, then we're half and half, right?
Yeah, but then you're...
So I'm running at 50% utilization in both
I see you
yep.
rearrange.
Okay. Yeah.
X of I equals x of 0.
If x of I, well, if x of I equals x of 0, you're either going to be all true or all false, right? So I'm going to run at 100% utilization because everybody's either going to go true or false, and then the other block gets skipped.
You could make it if I is 0 mod 8.
I is mod 0 mod 8, or let's say I change my input data such that every 8th item is going to trigger a true and all other ones true. Okay, so that'll get me 1 orange bar and 7 blue bars. I'm still not guaranteed. If those are equal cost things, I'm running at 50% utilization. Because half the time I'm 7/8, so the other half the time I'm at 1/8.
I thought it was with just an if statement and no else, so we're only running the if. That's what we were discussing.
Oh, I see. If you're only running the if. Okay, yeah, if you're only running the if, but I was thinking about if it's an if else.
Okay.
Yeah. But you're almost there. We've almost got it. So if you send 1/8 of the iterations down the if, 7/8 down the else, I'm still at 50% utilization unless we make some assumptions about the cost.
Yeah, the if statement take too long and the else statement.
If I send 1 iteration down if, and if is a billion instructions, and 7/8 down else, and that's the cheat path, which is almost the same basically as what you were doing. Yeah, exactly. So you see that? So I can make this chip with an if else run at 1/8 performance. And it's by essentially making the if clause very cheap, the else clause very expensive, and making sure when I'm running the if clause, only 1 out of 8 are actually running. But yes, so that is conceptually equivalent to your suggestion. Okay. This can be a problem, right? And on modern Intel hardware and AMD hardware, the vector width is 8. So on modern GPU hardware, that vector width could be as high as sometimes 32. So you might be like, well, if I mess things up, if I'm running at 132 of my total peak performance, that's a little frustrating sometimes. Okay. Just some terminology. You'll hear, especially if you read a lot of GPU programming stuff, you'll hear people go, you have to have coherent execution, you have to have coherent execution. Coherent execution is just a kind of a jargon and slang for saying, I have a program where all of the iterations of my loop, everything that's going on, needs the same instruction stream. And the lack of coherence is often called divergence, meaning like you think about it as like different control paths are needed. So divergent code will not run well on a SIMD architecture like this. Coherent code will run at high utilization. And here, this slide's just some extra facts that you can see on your own, where widths vary from about 4 wide SIMD on mobile chips, especially a lot of the ARM SIMD instructions, all the way out to about 32 wide SIMD on a modern high-end GPU. Okay, I will create a supplemental video talking a little bit about some slight differences between how GPUs implement this concept and how CPUs implement this concept. So I'll talk about it. I'll do an offline kind of just watch the video to get into that. Okay, so this is kind of interesting. We have 3 different ideas that we're mixing and matching together. They are orthogonal ideas. We have the idea of superscalar execution, which is a hardware implementation detail that requires no change to the program at all, which is if there are independent instructions in one instruction stream, the hardware figures it out and can execute 2 of them in parallel, inside the same core, inside the same instruction stream. We talked about SIMD, which is the program itself, most of the time, says, here are 8 operations or 32 operations that can be done in parallel. I have 1 instruction stream, usually. and it's just issuing these vector or larger operations. Again, with an asterisk on, I will clarify that statement's not precise for GPUs, but conceptually it's the same. And then you have the idea of multi-core, which is taking one of these cores that can run one instruction stream, maybe with vector instructions, maybe with superscalar, and copying that as many times as you have the resources to fit on a chip. So here are some examples, right? This processor, one core, superscalar. This processor down here, two cores, no vector, no superscalar. This processor here, 4 cores, 8 wide vector, no superscalar. And I can keep mixing things together. Like if I had to draw a diagram of the myth machines, not quite that, 4 cores, 3-way superscalar, 8 vector. 4 cores, every core can run 3 instructions per clock. Those instructions might all be vector instructions. NVIDIA GPU. About 80 of these cores. Each one of those cores has about 128 ALUs that are actually organized in 32 wide SIMD instructions. All the same ideas, just different scales. Some of these scales cause Keynote to crash because you can't draw the diagram. Yeah.
I see only one execution context, but shouldn't each
per core
fetch and decode have an execution context?
Superscalar execution is the core is given one thread. That thread has a sequence of instructions. If it finds one, because those instructions are in one thread, they're all reading and writing the same registers. There's only one thread, one execution context. If there happens to be the ability to find a couple of those instructions that can be run in parallel, this chip may find up to 3.
Just clarifying, how many vectors does one core run in this type?
4 cores. So often I want you to think about what's going on in a core, because like multi-core is just replicating things. Inside a core, I have one instruction stream. Registers right here. This core is running instructions in the instruction stream. Every ticket runs the next one. If it happens to find instructions that are independent, maybe it can run 3. If those instructions are 8 wide vector instructions, you'll get 8 wide vectors. So if you count here, there's 24 execution units. Peak performance of this core is 24 operations per clock. Peak performance of this chip is 4 times 24, 96 operations per clock. Okay? Peak performance of this chip is 128 times 80, and I can't do the math, operations per clock. Okay? Yes?
8 wide vector operations.
An 8 wide, like I want, I want you to think about an 8 wide vector instruction as an instruction, just like there's an add instruction. And an add instruction usually is add this scalar register to this scalar register, which means like add 42 and 10, and you get 52. A SIMD vector instruction is an instruction that says, please add this 8 wide vector to this 8 wide vector, element-wise. So a single instruction does 8 scalar operations. Imagine you're writing code in NumPy or PyTorch, and you have an 8 wide tensor and another 8 wide tensor, and you use the plus operation. That's a machine instruction. Okay. Yep.
When will this change? Like when did this change happen? That we move from this vector style process?
On x86, it was something called SSE instructions, and I don't know. They were 4 wide. I feel like they were probably early 2000s. Yeah. And they were 4 wide for RGBA for simple graphics operations. Yep. Okay. So I've kind of beaten in early in the lecture about the effects of latency, right? And we motivated caches as being this thing in a processor that is critical to not running at 250th of peak performance waiting on these things. And I also told you a little bit about, well, one of the major hogs of resources in a modern chip is putting these big caches everywhere you can in order to avoid stalls due to memory, right? And we talked a little bit about this access pattern where even though it was like really predictable and going right through the array, when we came back around, we still missed. We still missed, even though. So another thing that processors have in them, in addition to caches, is they actually have prefetchers. They actually analyze your program in the same way that they're looking for independent instructions in superscalar. They might look at your access pattern and go, I'm pretty sure you're going to be accessing this variable next, so I'm going to go ahead and preload that address for you. And so in a predictable access pattern like I just showed you here, where we're kind of running right through the loop, it's very possible that this may not, you got to fix that, it's not a conflict miss. It's very possible that that last load might have been predicted and actually might be there. But not all code runs like this, right? Like sometimes it's hard to predict something. Like imagine you're walking through a linked list, or imagine you are, you have some value and like you just computed a value and you're going to do an array lookup based on that value. A very common thing is like, give an array of indices, go look up the data at that index or something like that. So you can't, in these throughput computing ideas, you can't really assume that you can predict what's coming. And in order to make room for all of these cores, we might have taken out of the prefetching logic. We might have shrunk the size of the cache. So we've made it even more likely that we're going to take cache misses. Yet we packed the machine full of ALUs, which means we're going to make even more memory accesses and need to make them even faster to keep all these things busy. So we've really created ourselves a little bit of a problem here. We have these amazing processors that have all this stuff, yet they're waiting on memory. And so in my house tonight, I had a PhD student graduate a couple weeks ago, and we're inviting him and his girlfriend over for hot pot. And so there's going to be like a lot of prep going on. And so I want you to think about some real life examples. Let's say you're cooking in a kitchen. Let's say you're doing your laundry tonight because it's already day 4, so might be onto that. How many of you, when you're doing your laundry, you put the load in the washer and sit there and wait? How many people start boiling water and sit there and wait until it is ready before you put the food in? What do you do instead? I mean, maybe some of you do wait, I don't know. If not, you're going to come away from this class with a good life hack. So what do? You put your laundry in, you boil your water. What's going on? You sit around and wait? I mean, you watch all of my lectures on 2x, so I know you don't sit around and wait while you're... So what do? Sorry?
Something else.
You do something else, right? And you do your homework in 149. So the main idea is if you know something that you need to be done is not going to be done for a while, you just go do something else. Now that means you have to have something else to do. Like maybe all of your lives are such that, given anything else I have to do, I'd rather sit here and wait. But most of us have multiple things that we can do that we'd rather do. So this gets to the last idea of today. We're going to build processors that, remember, I just gave you a chip that, what did I say? It had 16 cores times 8 wide SIMD, so it had 128 execution units in it, which means it can do 128 things at once. But imagine you're doing some machine learning operation. Imagine you're processing a 4 megapixel photo off your iPhone, or I guess it's 8 or 12 these days. You have millions of pixels. You have way more things that you need to do than the things you can actually do at once. And so if you're going to sit there and wait on some of those things, let's just start working on something else. Okay, so here's the main idea. We're going to take that core that we had. Notice that in this diagram, it's a single instruction stream. It's got no superscalar, 1 instruction per clock, but I'm going to allow that to be a vector instruction just for the sake of things. Okay, and now what I'm going to do is I'm going to take the execution context, the registers, and the address space associated with them, and now I'm going to duplicate this. Okay, so remember I said that an instruction stream, the execution context represents the state of the instruction stream. Or in other words, we could say the state of a thread. Now what I'm going to do is the processor, the orange and the yellow is staying exactly the same. But I'm going to give that processor the ability to hold state for 4 instruction streams, for 4 threads. Okay? So we're going to start executing normally. So now we're going to say, look, for this processor, your program is going to say create 4 threads now. For 1 core, 4 execution context, here, have 4 threads to do. And so the processor is going to move along and it's going to run a thread. That's what I'm kind of trying to show you here. It's going to run this thread. Maybe it's executing 70 instructions, and at some point it gets to a load, cache miss. This thread cannot make progress for a long time. Let's say this is the point at which it becomes runnable again because the data came back from memory. That was the 250 cycles that we were waiting. Okay? So do you think this core is going to stay idle? Nope. The minute it's like, I can't make any progress because I got to wait, I'm like, I got 3 other threads that I can go make progress on. So we're going to swap. And when I say swap, I'm talking about the hardware just starts executing instructions from the next thread, like no delay or anything. It's just, oh, I can't make any progress with this instruction stream. I've got another one sitting here. Next cycle, I'm going to run that one. I'm going to run whatever's available. And then maybe that one stalls, but we got another one. Maybe that one stalls. We got another one. By the time that 4th one has stalled, we are past the point in time where this one is ready. So we can get going again. We can just start working on that other thread. And let's say it finishes, and we move on and so on. What is the utilization of this processor? 100%. What is the latency of actually finishing any one thread? It's actually longer because it actually had this time where it could have started running here, but it actually runs here. Okay? That's the last big idea here. Is we're actually slowing down the amount of the wall clock time to get anything done in order to get everything done quicker because we're running at 100%. I'll stop there. Okay, so we'll review this again next time. We'll start and then we'll get into combining the memory and the superscalar. But you have everything you need to get started and do 90% of your homework assignment.